Myself, I'm Ganga Bhavani, Assistant Professor in EC Department of IARE. So today we'll discuss a topic, LC type oscillators from analog and pulse circuits. So this is a basic general form of an LC oscillator. In the last class we have seen RC oscillators, that is Wien bridge oscillator and RC phase shift oscillator. As we know, RC oscillators are basically used to generate low frequency signals. So if you want to generate frequencies, sinusoidal signals of higher frequencies, then we can use LC oscillators and crystal oscillators. So this is a general form of an LC oscillator. Okay, basic amplifier and impedances arranged in this form. Okay, so to the terminal 1, I'm giving across the terminals 1 and 3, I'm connecting Z1. Here 3 is connected to ground. So across 1 and 3, I'm giving Z1. And across 2 and 3, it is Z2. And the impedance between 1 and 2 is Z3. So depending upon which type of LC oscillator you are using, these values of Z1, Z2 and Z3 will change. But in general, an LC oscillator basic block diagram is this one. Okay. Impedance Z1 across 1 and ground. Impedance Z2 across 2 and ground. And between 1 and 2, the impedance is Z3. Okay. So the oscillators which use the elements L and C to produce oscillations are called as LC oscillators. As the name itself suggests, LC oscillators are the oscillators in which the inductor and capacitor are used to produce the oscillations. So in the place of that amplifier in the block diagram, we can use any active device like BJT, FET, op-amp or vacuum tubes. Okay. And here Z1, Z2, Z3 are reactive elements used for feedback tank circuit which determine the frequency of oscillation. So the Z1, Z2 and Z3 itself will determine the frequency of oscillation. And voltage across Z1 is the feedback voltage, voltage across Z2 is the output voltage. So here if you see, voltage across Z1 is feedback voltage Vf and voltage across Z2 is the output voltage V0. Okay. So if we try to write equivalent circuit of an oscillator, okay, so in place of amplifier, I'm just replacing it by HIE, okay, approximate equivalent circuit of a transistor. HIE, this is impedance, and HFE is the current source, HFE into IB. Okay, so you'll have Z1 impedance, Z2 and Z3 across 1 and 2. Okay. So the overall impedance of this circuit. Now, if I try to write its equivalent, okay, you can see that Z1 and HIE are in parallel first. Okay. So if I just draw one block, Z1 parallel to HIE, okay, and then this block on one end it is connected to ground, okay. On the other end, it is connected to Z3, okay, and here HFE, yeah. What about this one? Z2, here you'll have Z2, okay, and other end of Z2 is given to this point, Z3, okay now. Yeah, here you'll have Z1 parallel HIE plus Z3. Okay. Now you just see. Now this Z3 and Z1 parallel HIE are in series. Okay. So we can write it as Z1 parallel HIE plus Z3. This is one block, okay. One end of it is connected to ground, and other end you have again Z2, okay. Now again we see that one end of the two impedances are connected and the other ends are given to ground. So it is again understood that this Z1 parallel HIE plus Z3 is in parallel with Z2. Okay. So overall impedance is given by ZL equal to Z1 parallel HIE plus Z3 in parallel with Z2. Okay. So we shall try to simplify this. So ZL is equal to Z1 parallel HIE plus Z3 parallel Z2. So parallel combination of Z1 and HIE, what do we get? Z1 into HI, Z1 Z2 by Z1 plus Z2. So it is Z1 into HIE by Z1 plus HIE plus Z3. Again, this entire thing is in parallel with Z2. So if we just take LCM Z1 plus HIE, we get Z1 HIE plus Z3 into Z1 plus HIE whole divided by Z1 plus HIE in parallel with Z2. So on simplification, you see that now this thing is in parallel with Z2. So it is again Z1 parallel Z2 form. Okay. So if we treat this complete thing as one impedance, this is in parallel with Z2. So Z1, Z2 by Z1 plus Z2. So this impedance into Z2 divided by this impedance plus Z2. Z1, Z2 by Z1 plus Z2 form parallel combination. So on further simplification, you can see that this ZL will be equivalent to Z1 HIE plus Z3 into Z1 plus HIE into Z2 by Z1 HIE plus Z3 into Z1 plus HIE plus Z2 into Z1 plus HIE. So this is the overall impedance ZL of the oscillator. Okay. Now, how do you define gain of the CE amplifier? Gain of the CE amplifier can be calculated as AV equal to minus HFE by HIE into ZL. Okay. So by applying voltage division rules, the same circuit, if I just simplify it and draw, it will be something like this. Z1 HIE. We will just go back to this previous figure. Z1 HIE. This combination is connected across. One end of this is connected to ground, other end is given to Z3. Okay. Z1 HIE. This combination is given to ground on one side and on the other side it is connected to Z3. Okay. So, see, Z1, HIE, Z1, this combination is connected to ground on one end, on the other end it is connected to Z3. So now you just see that by applying voltage division rule, how do you write the equation for VF? This is nothing but VF. So VF is equal to V0 into Z1 parallel. See, these two are in parallel. So V0 into Z1 parallel HIE by Z1 parallel HIE plus Z3. So we are just applying voltage division rule to this circuit. So you get VF is equal to V0 into Z1 parallel HIE by Z1 parallel HIE plus Z3. So, but we have a relation VF by V0 is equal to nothing but beta, because since VF is equal to beta into V0, we have VF is equal to beta into V0. So from this, beta is equal to VF by V0. So beta equal to VF by V0 equal to Z1. So Z1 parallel HIE is what? Z1 HIE by Z1 plus HIE divided by Z1 HIE by Z1 plus HIE plus Z3. So on further simplification, this is equal to this one. Z1 HIE by Z1 HIE plus Z3 Z1 plus Z3 HIE. So finally you will get this value for beta. So according to Barkerson criteria, to generate oscillations, modulus of A beta should be greater than or equal to 1. So A equal to what? From the previous equation as we have derived, A equal to what? Minus HFE by HIE into ZL. So minus HFE by HIE into minus HFE by HIE into this complete thing is equal to ZL. Okay. So AV equal to this one and beta is equal to, from the previous equation what we have seen, beta equals Z1 HIE by Z1 HIE plus Z3 into Z1 plus HIE. So this is a value of beta. So using Barkerson's criteria, AV into beta should be equal to 1. So AV into beta equal to 1. If you simplify further, you'll see that the general equation is given by 1 plus HFE into Z1 Z2 plus Z1 Z3 plus HIE into Z1 plus Z2 plus Z3 equal to 0. Let's just simplify this equation, taking cross multiplication. Taking all the terms to one side, you will have the final equation of LC oscillator is this one. Okay. So, using this general equation, now we will have two types of LC oscillators. Okay. That is Colpitt's oscillator and Hartley oscillator. Depending upon the impedances what you are taking in place of Z1, Z2 and Z3, you have two types of oscillators. Okay. So in both the oscillators, we'll use this general equation only to derive the frequency of oscillations. So if Z1, Z2 both are equal to L and Z3 equal to C, then it is Hartley oscillator. It's in this block diagram. Okay. If Z1, Z2 both are equal to L, that is inductor, and Z3 is equal to capacitance, then the oscillator so formed is called as Hartley oscillator. On the other hand, if Z1 equal to C1, Z2 equal to C2, and Z3 equal to L, that is inductance, then the so formed oscillator is called as Colpitt's oscillator. So we shall see both in detail. So coming to Hartley oscillator, see the basic amplifier that is in CE configuration is given here. Okay. So across this terminals, terminal 3 is given to ground. Between 1 and ground it is L1. Between 2 and ground it is L2, and across 1 and between 1 and 2 you are giving capacitance, that is Z1 equal to L1, Z2 equal to L2, and Z3 equal to C. Okay, that is you are using inductors and capacitors in place of Z1, Z2 and Z3. Now from the general equation, we have seen the general equation. Okay, this is the general equation: 1 plus HFE into Z1, Z2 plus Z1, Z3 plus HIE into Z1 plus Z2 plus Z3 equal to 0. I've just rewritten this general equation here. So from this general equation, okay, now I'm using L1 as Z1. So what is Z1 equivalent impedance of, when you're using inductance, how do you write its impedance? Z1 equal to J omega L1. Similarly, Z2 equal to J omega L2. And if it is capacitance, we write Z equal to 1 by J omega C. So here Z3 equal to 1 by J omega C. Z3 equal to 1 by J omega C. Now substituting all these values of Z1, Z2 and Z3 in this original equation, general equation, minus of 1 plus HFE into Z1 is J omega L1, J omega L2. Product of these two will be J square is minus 1. So it is minus omega square L1, L2. Okay. So this minus I am writing here, minus of 1 plus HFE omega square L1, L2 plus Z1, Z3. Z1, Z3, if you multiply these two, what do you get? J omega get cancelled. You will have just L1 by C plus HIE into Z1 plus Z2 plus Z3. So if I take J omega common in all the terms, J omega into L1 plus L2 plus last one I am writing 1 by J omega C as it is. Okay. On further simplification of this equation, you will get finally minus of 1 plus HFE into omega square L1 L2 plus L1 by C plus HI into J omega L1 plus L2 minus J by omega C equal to 0. Okay. So if you want to derive the condition frequency of oscillations, okay, if you want to derive the frequency of oscillations, what is the condition we follow? That is, at resonant frequency, imaginary part should be equal to 0. So from this above equation, what are the imaginary terms? See, J terms are only up to this. The rest all are real. So now if imaginary part is equal to 0, we write HIE omega into L1 plus L2 minus 1 by omega. So if you take J common here, plus J into HIE omega into L1 plus L2 minus 1 by omega C equal to 0. Okay. So this will be the imaginary part. So equating this imaginary part to 0, okay, what do we get? HIE, okay, HIE is not equal to 0. So what can we write? Omega into L1 plus L2 minus 1 by omega C equal to 0, or simply omega into L1 plus L2 equal to 1 by omega C, or L1 plus L2 equal to 1 by omega square C, or omega. From this what can we write? We can write omega square equal to 1 by L1 plus L2 into C. So omega equal to 1 by root over L1 plus L2 into C. And as we know, f omega is equal to 2 pi f. So f is equal to 1 by 2 pi root over L1 plus L2 into C. This is the frequency of oscillations. Okay. Now, if L1 plus L2 equal to L equivalent, then we can write F equal to 1 by 2 pi root over L equivalent into C, where L equivalent is equal to L1 plus L2. Suppose if you are considering or if you are taking mutual inductance also into account, then we can write F is equal to 1 by 2 pi root over. So L1 in place of L1 we write L1 plus M, and in place of L2 we write L2 plus M. So what on the whole you will get L1 plus L2 plus 2M into C. This is the frequency of oscillations. Now to find the condition for oscillations, we will go back again to the general equation only. Okay, in the general equation we will substitute this frequency of oscillations, that is again taking imaginary part equal to 0 and substituting omega equal to 1 by, or simply omega square, 1 by omega square C equal to L1 plus L2. See, from the general equation we have this, okay. So minus of 1 plus, and equating imaginary part to 0, you will have minus of 1 plus HFE into omega square L1 L2 plus L1 by C equal to 0, or taking these terms on the other side, L1 by C equal to 1 plus HFE into omega square L1 L2. Okay. But what did we get finally? Omega equal to 1 by root over L1 plus L2 into C. Or simply I can say omega square equal to what? Omega square equal to what? Omega square equal to 1 by L1 plus L2 into C. So replace that omega square here, 1 by H. So from this equation what do we get? 1 plus HFE into omega square. What is omega square? What is omega square? 1 by L1 plus L2 into C. Okay. This is omega square. And on numerator you have L1 L2 equal to L1 by C. So cancelling C on both sides and cancelling L1 also on both sides, what do we get? 1 plus HFE equal to L1 plus L2 by L2. So it's nothing but L1 by L2 plus 1. Okay, this is 1 plus HFE. So once you get 1 plus HFE equal to L1 by L2 plus 1, on the other, in other words, you can say HFE equal to L1 by L2. So this is a condition required for oscillations. HFE should be equal to L1 by L2. And on the same as for frequency of oscillations, if you want to include mutual inductance also, then HFE must be equal to L1 plus M by L2 plus M. So this is regarding Hartley oscillator. Same basic block diagram only, but in place of Z1 you will have L1, Z2 equal to L2, and in place of Z3 you are using capacitance C3. So you will write its equivalent impedance and finally find the frequency of oscillations, and also we have seen what is the condition for oscillations. Okay. Now, if we go for the Colpitt's oscillator, as I told, here you will be using in place of Z1, Z2 you will have capacitance. So this is Z1, this is Z2 and this is Z3. Okay, same basic amplifier, just you are replacing Z1 by C1, Z2, C2 and Z3 is here, inductance L. Okay, so same as how we have seen for Hartley oscillator, for Colpitt's oscillator also we will try to derive frequency of oscillations and condition for oscillations. For that what we do generally, we go for the general equation of LC oscillator. Okay, so the general equation of LC oscillators, as we have seen, this was the general equation. Now I'll substitute Z1 equal to 1 by j omega C1, Z2 equal to 1 by j omega C2 and Z3 equal to j omega L. Substituting all these three values in the above equation, okay, finally on simplification you will get minus of 1 plus HFE into Z1, Z2 is what? 1 by j omega C1 into 1 by j omega C2. Okay, j square is minus 1, so here you have minus, okay, omega square C1, C2 plus Z1, Z3, j omega L into 1 by j omega C1. So j omega get cancelled, you will have L by C1 plus HIE into Z1 plus Z2 plus Z3. So it is 1 by j omega C1 plus 1 by j omega C2 plus j omega L. Okay. So on further simplification, finally we will get this equation HIE into. So if you add these three, Z1 plus Z2 plus Z3, then you are going to get this as a result. Okay. Then, so to find the frequency of oscillations as we have done earlier, we'll just equate the imaginary part to 0. So what is the imaginary part in this equation? HIE omega into L minus 1 by omega square C2 minus 1 by omega square C1 equal to 0. Okay. So equating, taking all the negative terms on the other side, you'll have L equal to 1 by omega square C1 plus 1 by omega square C2. Or taking omega square to the left side, you'll have omega square L equal to 1 by C1 plus 1 by C2. Okay. If you let 1 by C1 plus 1 by C2 equal 1 by C equivalent, then C2 plus C1 by C1 C2 equal to 1 by C equivalent. So simply you can say C equivalent equal to C1 C2 by C1 plus C2. Okay. Is equal to 1 by C equivalent. So C equivalent equal to C1 C2 by C1 plus C2. So omega square L equal to 1 by C equivalent, or omega square equal to 1 by L into C equivalent, or simply to say omega equal to 1 by root over L into C equivalent. And replacing omega by 2 pi F, you will have F equal to 1 by 2 pi root over L into C equivalent, where C equivalent is equal to C1 C2 by C1 plus C2. This is C equivalent. So this is how we derive frequency of oscillations for Colpitt's oscillator. Okay. Then we shall also see how we are going to derive the condition for oscillations. So to derive the condition for oscillations, we'll take again the general equation only. In the general equation, we'll replace this value of omega square. Omega square is equal to, omega square L equal to 1 by C1 plus 1 by C2. We shall just see. From the general equation, you have this equation and equating imaginary part to 0. Finally, you are left over with this. So if you rearrange the terms, okay, L by C1 equal to 1 plus HFE into 1 by omega square C1 C2. Right. So if you cancel C1 on both the sides, you'll just left over with L equal to 1 plus HFE into 1 by omega square into C2. So 1 plus HFE equal to 1 by L into omega square C2. 1 plus HFE equal to L into, what is omega square? So in the previous equation you have seen omega square is equal to 1 by L into 1 by C1 plus 1 by C2. So 1 by L into 1 by C1 plus 1 by C2 into C2. So 1 plus HFE equal to, right, see, L and L will get cancelled on both this numerator and denominator. So you are finally left over with, so this is equal to what? C2 by C1 plus C2 by C2. So this is nothing but 1 plus C2 by C1. So 1 plus HFE equal to 1 plus C2 by C1, or HFE equal to C2 by C1. This is a condition for oscillations. Okay. So far we have seen what is an LC oscillator, an oscillator in which L and C are impedances, okay, or the reactive elements. Such oscillators are called as LC oscillators, and LC oscillators are basically used to generate high frequency signals, high frequency sinusoidal signals. Okay, so we have seen the general block diagram of an LC oscillator, derived the general equation. Then for each Hartley oscillator, we have choose the proper impedances Z1 equal to Z1, Z2, both are inductors, and Z3 is nothing but capacitance, that is Hartley oscillator. Coming to Colpitt's oscillator, Z1, Z2 are capacitors and Z3 is inductor. So in both of the cases, what we have done, we have just, from the general equation only, we have substituted the values of Z1, Z2, Z3, and then finally equated it to, correct. After writing the general equation and substituting the values, now to find the frequency of oscillations, we have equated the imaginary value to 0. From that, we get the frequency of oscillations. And again, from we have finally seen the condition for oscillations also, for both LC oscillator and for both Hartley oscillator and Colpitt's oscillator. Frequency of oscillations for Hartley oscillator is given by 1 by 2 pi root over L equivalent into C, where L equivalent equal to L1 plus L2. Coming to Colpitt's oscillator, the frequency of oscillations is given by 1 by 2 by root over L into C equivalent, where C equivalent equal to C1 C2 by C1 plus C2. Okay, and frequency of oscillations, it is given by H1 HFE equal to, for Hartley oscillator it is L1 by L2, HFE equal to L1 by L2, whereas for Colpitt's oscillator it is HFE equal to C2 by C1. Okay, this is all about Hartley and Colpitt's oscillator. So this is a reference book that I have gone through, Jacob Milliman, Christus C. Harkes, that is Integrated Electronics. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.